All right, so the
Okay,
system,
it's on. Okay, go ahead.
see what I did there? All right, this is a Homework 2 report uh, presented by Tim, Wendy, Karen, Ting, Zhu, and Yuzu. We're I'm gonna briefly cover Homework 1, like how, because that's what we're building off in Homework 2. So we did our exercise 1 where we like envisioned the what we were gonna build, and like we had system context diagrams, broke down on like what the technical environment looks like and what the domain knowledge that we're building it with. Um, break down all the system features, use cases. This was all part of exercise one, just trying to get a good understanding of what we're building and like what's required of it. Um, and a lot of the artifacts produced by exercise one, your scenarios for all the different NFRs. Then we moved on to exercise two. This is where actually the real business meetings happened. Stakeholders stepped in to talk about their viewpoints, and so based on that, we figured out what our architectural drivers were going to be, and obviously the requirements given by the customer was yeah. The at least the five requirements we had from the customer, we added one of our own and their business value and architectural impact. And these were all the artifacts that were produced by exercise two. So this is the main part of homework two, the ADD iteration one. A lot of the artifacts used in the past exercises help us build off of what we're gonna do in this exercise. So we do a brief introduction, like how we're choosing to, what we need, like we're for the ADD iteration, what we need to make sure is all the requirements are there, like all the everything that we need for the entire iteration, we have that. So that's basically what we do in our step zero. Functional requirements we already came up with are here. We have design constraints, we have our quality attributes, and the stakeholder prioritization, like so we know what we need to work on. And then so this is the rationale we have for that. I want to do step one as well. Yeah, so this is also a part of the exercise three, just like getting warmed up for the ADD iteration. We we make sure like we have all the requirements, we have all the previous artifacts, we have the use cases and the design constraints, and we just build off of that.
Okay. Um, Now I'll be presenting step two. Basically, for the first iteration, we didn't decompose the entire FDOM system because this was the initial architecture design phase and no architectural structure had been defined yet. In step three, sorry. We identified the system's primary architectural drivers using a utility tree. The highest priority drivers were safety, availability, followed by accuracy, monitorability, and interoperability. These drivers reflect the system's need to safely detect, assess, and respond to airborne threats while maintaining reliable operation. And then from then, we created an ADRT table. Um, to map each quality attribute scenario to appropriate tactics and architectural patterns. As you could see, we selected publish, subscribe, and SOA patterns along with some tactics such as monitor active redundancies. And then based off this ADRT, we built the pros and cons matrix, PCM, um, to compare strengths and weaknesses of each pattern against the architectural drivers. And the analysis showed that the publish subscribe pattern was actually like the best for like strong support for real-time notifications, redundancy, and monitoring, while SOA improves integration, modularity, and future extensibility. And yeah, it's basically all for me. Oh, and yeah, next person.
Who is the next person?
Yeah, I'm waiting for the access. Okay, so next is our step 5 of iteration 1. Since we're decomposing the whole system and our pattern is selected, so we decompose the system into this following child elements. And they are in charge of different responsibilities. And here is the attributes architecture drivers assigned to each of the element. And this table here is the functional requirements allocated to each modules. And here is our module view, and this one is the latest diagram. So as you can see, every services communicate with event bus here, and some services subscribe it. So the whole information is flowed in different services through the event bus. And the next one is our component and connector view. So every services is connected in such way. And here is where each of the element is deployed. And so here is our design decision and considerations. So it's like thread processing was separated into thread classification and accuracy verification services to improve accuracy and simply maintenance and the following things. And that is step 5.
Okay. Next is me. So, okay. Okay, for this part, I will present step 6, which is about interfaces. And after we decompose the system in step 5, we need to define how those child elements communicate with each other. So step 6 is not about detailed code level APIs yet. It is about the interface contracts between architectural elements. For each interface, we identify the provider, the consumer, the main data being exchanged, and the quality attribute the driver it supports. In the first iteration, we decompose the whole FDOOM system so the interfaces are at the system level. For example, the sensor data input. The sensor-based data input interface receives raw data from radars, satellites, detectors, and trackers. The message translation interface converts external formats into the internal FDOOM threads event format. This is important for interoperability because different external systems may use different data formats. Another important interface is the thread event publish interface. This one uses the event bus to publish normalized thread events, sensor schedule events, and alert events. This supports the publish subscribe pattern. It also helps availability and monitorability because multiple services can receive important updates without being tightly connected to each other. We also define interfaces for clarification, accuracy verification, defensive decision-making, safety validation, device command monitoring, upgrade display, and shared data access. These interfaces show how the main FDOOM services work together from detection to decision, then to operator display or device control. Okay, next one.
Okay, and now at the step 7, the verification. And okay, now I can control. This section, we verify the architecture decomposition using the ATD and across all the table dimensions, the quality attributes, the verification criteria, and the evidence risks. And for the safety, we're required to ensure the engagement command only executed if safety validation confirmed the interception is outside safety zone within 2 seconds. And we use safety validation and defense recommendation service to ensure that, and the evidence is pre-execution blocking before reaching control services. The risk is increased latency under high concurrency. And for the availability, we enable the requirement by active redundancy, event bus, and sensor integration services to make sure the maintain 99% uptime and perform failover within 5 seconds when sensors fail. And we have evidence that the heartbeat monitor and replicated streams, the risk is even event bus congestion delaying failover. For the accuracy, we use multi-sensor fusion and layered validation services to ensure 99% classification accuracy. And the evidence is consistency checking before recommendation. The risk is conflicting sensor data, reducing confidence. For the monitorability, we're using monitor logging, event bus, and dashboards to detect the faults within 15 seconds and the report within 5 seconds. Event-based alerting. Risk is high event volume delaying alerts. And for interoperability, we use the adapter service and SOA interface to make sure the external data is translated and integrated with 3 seconds. The evidence is conversion into internal event schemas. And the risk is parting latency from complex format. And overall, this table shows the full traceability from requirements to architecture, evidence, and risk across all QA. So that's all for step 7.
Okay, and then now I will be presenting iteration 2. So for step 2, we had to choose an element to decompose, and we chose the safety validation service, given that safety is one of the most critical concerns in the FDOM system. And it was selected, or this element was selected based on the organizational criteria, given that protecting human life and preventing unsafe engagements are the primary priorities. In step 3, we refine the architectural drivers into 3 safety-focused scenarios. The first driver requires a system to assess collateral risk before engagement and ensure that no campus buildings, students, faculty, staff, or designated safety zones are endangered. The second driver requires a system to validate all system rules or safety rules, engagement policies, and operational constraints before transmitting a command to an anti-air strike device. And the third driver focuses on human oversight by requiring a defense operator to review, approve, or reject recommended actions before execution. In step 4, we developed the ADRT to identify the architectural patterns that best support these 3 refined drivers. For collateral risk assessment and operator notifications, we selected the publish subscribe pattern. Because it enables real-time monitoring and rapid distribution. And we also selected the SOA pattern to organize risk assessment, validation, approval logging, and policy enforcement as independent services can be developed, maintained, and reused separately. And then next, we evaluated these patterns using the pros and cons matrix again. And yeah, the analysis just showed that publish subscribe provides an efficient method for event distribution and immediate notification, while SOA improves modularity, maintainability, and flexibility. And yeah, so based on these ADRT and PCM results, we selected a combination of publish, subscribe, and service-oriented architecture for the safety validation service.
Okay. Next is our step 5 of iteration 2. And based on the previous patterns we selected, we decompose the safety verification module into the following child elements. And also, as mentioned as previous iteration, we still allocate the responsibility and functional requirements into these modules. And so here is a module view. And here is the component and connector view and allocation view. That's it.
Okay.
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 I'm waiting for the control. Okay. Okay. Well, in the second iteration, we focus more deeply on the safety validation services, since this service is very important for preventing unsafe defenses actions. We decomposed it into smaller tracker modules. This includes the interception area tracker computes, safety zone tracker, civilian risk tracker, facility damage risk tracker, and so on. The interfaces in iteration 2 are more detailed. For example, the engagement validation requires the interfaces starts the safety validation process. It passed data such as the threat ID, recommended action, projected interception area, device type, and the operator ID to the safety decision engine. Then each tracker has its own interface. The interception area tracker interface checks whether the projected interception point and the debris radius are safe. The campus safety zoom check interface checks if the action overlaps with restricted campus area. The civilian risk check interface estimates risk to students, faculty, staff, and nearby civilians. The facility damage risk interface checks possible damage to buildings and facilities. The rule and policy validation interface checks engagement rules and operator permission. After these checks are completed, the safety decision engine combines the results. Through the safety decision interface, it returns an approved rejected interface. It turns L holds decision with a reason. Then the safety result reporter sends the result to the operator dashboard, monitoring service, and login and audit service. This makes the decision visible to the operator and also keeps an audit record. The main reason for this interface design is separation of responsibility. Each checker focuses on one type of safety concern. This makes the safety logic easier to understand and easier to change later. Also, no defensive action should be executed before these safety checks are completed. So these interfaces directly support and safety drivers. They also support monitorability because the system can report and record why a command was approved or blocked. Overall, step 6 helped us connect the decomposition from step 5 to actual communication between components. It also made the architecture more traceable because each interface can be connected back to quality drivers such as safety, interoperability, availability, monitorability, and accuracy. That's all.
Okay, let me scroll down to the verification part. Okay, for the iteration 2, we follow the same structure as before, and this time we have 3 QA to verify. And for the first one, the collateral risk check, we use pre-execution validation pipeline and safety validation, geospatial analyze, and decision gate to do that. And the evidence is geopatho safety zone checking performance and predict with blocking before command propagation. And the main risk is latency under high load and inaccuracy in prediction or geospatial data. And for the second safety scenario, the rule validation before engagement transmission, the system is supported by the safety validation service combined with the rule engine and policy enforcement layer. The evidence is rule evaluation and decision gate with rejection and notification when violation occur. The risk is outdated or inconsistent policy rules. For the third safety scenario, the human oversight and approval is implemented through the operator decision support module, monitoring and logging surface, and human-in-the-loop control layer. The evidence is the operator dashboard displaying recommendation and audit logging and decision and rationale. The risk is human response delay or operator overload, affecting decision quality. So that's all for step 7, the iteration 2 verification.
Mute. Okay. The last section has 7 parts, and it's about how we document the architecture of different stakeholder, not the design itself. We identify 5 stakeholder groups and picked 3 values to cover their needs, like the module value and for the structure, and the component and the connector value for the runtime communication, and the allocation value for the deployment. These 3 values gives a complete picture of a system, which is why we choose them. And the next part from the section 4 to 6, we walk through each of these values, and they all follow the same patterns and a short explanation of why that values was chosen. The first one is the module value. For this one, we have the 6-layer breakdown of the system, and the next one is a component and the connector value document. This catalog actually split into 2 parts: the components themselves and the connector tabs. And the last one is the allocation values. And let me show. Oh, sorry. Okay, this one. Okay. And the allocation value documents, instead of listing savers, it's organized by savers and showing what runs where, and all the sections 7 ties it all together by explaining these 3 values are very important, like the structure, runtime behavior, and deployment. And the architecture document is different from detailed design, since it focuses on major decisions rather than implement details. And the last part of our report summarizes the whole project. The architecture was built using attribute-driven design around 5 drivers, like the safety, availability, monitorability, and interoperability, using a layers architecture and the public subscribe and server-sovereign architectures. And safety was a top priority of our system, which is why we went back and decomposed the safety validation servers further in the iterations. And the main lesson was that the architecture is really about trade-offs and not just picking around the patterns. And the last part is about what we learned from this report and the conference list and our team chatter. Here's all of our report.
Okay, I'll stop recording.